Aloha class, ugly sweater day here at MCHS BC. Here we go. Improper integrals. Okay, that means integrals that are improper. Okay, I don't know about this dude, but I was taught, you pick up that box, you better keep those heels on that ground, right? You better keep the heels on that ground, right? And you get down there, you use those legs, get a little squatting action in. All right, here we go. Example 1. Okay, a little bit of an exploration before we get going here. And I plugged all this stuff into my calculator already, so you guys don't have to, okay? But it says evaluate by using your calculator. So let's go ahead and do that. If I plug this first integral in my calculator, I get 4.605. Okay, let's plug the second one into our calculator. I get 6.908. Okay, and now let's plug the third dude. Homie's trying to mess with my cable. Okay, plug the third one in there. I get 13.815. Okay, and then the question here is based on your values above, what do you think that integral equals? Well, I would say it's definitely going up. I go from 100 to 1,000 to 1 million, but it does incrementally go up. So my guess would be, hey, infinity. Or we would say in calculus that it diverges. Okay, it's divergent. Okay, it goes to infinity. Okay, now here let's look at a couple of other these guys. We have a new function now. It's e to the negative x. Okay, I plug in 100, I plug in 1,000. Let's see what's happening. Plug in 100 into that guy, little math 9 it. Booyah, 0.367. Let's plug in this other one, but put 1,000 in there. I get 0.367. Oh, snap. So what do I think this equals? Well, let's go a little crazy, maybe 0.368 or 0.367. And believe it or not, it does. Now the question is, that's pretty interesting because those two problems are very similar. However, there were different graphs that we were looking at. Okay, and let's sketch both of these graphs, okay? If I was to graph y equals 1 over x, right? We have a vertical asymptote. It's going to look something like that. Okay, if I was to graph y equals e to the negative x, okay, my graph looks like this. I have a y-intercept there, and my graph looks like that. If you notice, there's definitely a difference between the two. Now, we all know that this symbol right here means the area under the curve, and we're going to find the area of the curve from 1 all the way to infinity. Okay, and if you look at this first graph, the reason why it was divergent is because it looks like that area definitely goes to infinity. Now, the interesting thing about this graph right here, if we take the area from 1, is that this guy gets so close to the x-axis, it makes it converge. Okay, and we found out that this converges to 0.368, which, believe it or not, is the number 1 over e. So what we're going to explore in this unit is improper integrals. And believe it or not, just because we're going to infinity, it does not mean, it seems like a weird concept, but it doesn't mean that it's always going to diverge. If my graph gets to that x-axis super quick, okay, then it actually is going to converge to a specific value. And that's what we're looking at here in this BC topic. Okay, so let's just get after it. Okay, so how do we deal with infinite integrals of integration? Okay, if the integral from a to b of f of x dx exists for every b that's greater than a, then we evaluate by using the idea of a limit. Okay, and same thing. Okay, b to c, where b is less than a, same exact thing. We use the idea of limits. So how does this all work? Well, let's take a look at it, okay? Because we are not allowed to use our calculator on portions of that AP exam, right? Hum-hums, okay? All right, so let's see, how do we do this guy and use that little property we had up there? Well, I'm going to turn this into a limit. Okay, I'm going to get rid of that infinity symbol, and I'm going to take it as b goes to infinity, and I'm going to do it from the integral from 1 to b of x to the negative 3 over 2 dx, right? I'll rewrite that. Now let's go ahead and do this, okay? Limit, I'm going to go ahead and do the integral or the antiderivative, and the antiderivative of that guy would be, let's add 1 to it, so that'd be x to the negative 1/2, but then I have to divide by a negative 1/2, which would be the same thing as multiplying by negative 2. So then I get that from 1 to b. Okay, so now I'm going to go ahead and use my fundamental theorem of calculus, right, class? And if I do that, I get negative 2, and then I'm going to get a 1 over b to the 1/2 if I wanted to rewrite it. And then that would end up being a plus, plug a 1 in there, and I would get 2. Now, if you notice here, that b is in the bottom. So if you look at this, it's like going to be negative 2 over, because now I can substitute that infinity and over infinity to the 1/2 plus 2, which we all know is something divided by something huge, and that would be 1/2. That'd be 0 plus 2, which would be 2. Right? So that means if I was to look at that graph, it gets really close to the x-axis super duper fast. Okay, which is why it converges. So that converges to the value of x equals 2. Let's look at this next guy. Okay, it's an improper integral. Why? Because it has a limit that's infinity. So we're going to turn it into this guy, which will enable me to evaluate it. Okay, and I'm going to rewrite it as the integral from 1 to b. Let's rewrite this as x to the negative 2. Remember, we like negative exponents in BC Calc. Okay, now we're going to go ahead and find the antiderivative. Okay, the antiderivative, we would add 1, which would be that, divide by it, which would be a negative 1, right, class? And then we're going to go from 1 to b. Now we're going to use our fundamental theorem of calculus. What the heck was that? Okay, here we go. Let's go ahead and use that guy. And so what would that be? That'd be negative 1 over b, and then it'd be plus 1, right? And then we're going to plug in that infinity, which would be 1 over infinity, which would go to 0, plus a 1, which is equal to 1. So that guy converges to 1. How about it? Not bad, not bad. I can handle this stuff, right? Once again, BC topics, right? BC topics. Not bad so far. Let's look at the next one. Okay, once again, improper integral. What do we do if it's an improper integral? And sometimes you guys will want to do this without bringing out that limit. Now, in order to receive full credit on a free response question on the AP exam, you have to show that you're treating it as an improper integral. And the way we do that is we turn it into a limit, okay? Now let's evaluate this. So we're going to find the antiderivative. The antiderivative, well, once again, power rule, we add 1 to it, which is a negative 2. And I divide by that, which would be a negative 1/2. Go from 1 to b, fundamental theorem of calculus, right? Gets a little bit repetitive here. That'd be negative 1 over 2, and then that would be b squared on the bottom, right? And then plus a 1/2 when I plug in that 1. Once again, it'd be negative 1/2. Ooh, infinity squared. That's enormous. Plus 1/2, and so I get 0 plus 1/2. Oh, snap, that converges again. Now the question is, hey, do you see a pattern of all of these problems in terms of their exponents? And so let's look at all of those. And if you were like, hey, Mr. Tanaka, hey, Homer Holmes, every single one of those, the exponent is bigger than 1. Well, if they're all bigger than 1, then maybe that means it converges. And believe it or not, it does. Okay, we have this little factoid, okay, facty fact, okay, that if a is greater than 0, okay, so a's got to be greater than 0. And if you have the example of 1 over x to the p, which we had on all of those up there, okay, and if p is greater than 1, then it converges. Guess what, though? If p is less than or equal to 1, it diverges to infinity. These are called p series, okay, and p being the exponent there on that x variable down there. Okay, now more specifically, if a was 1, we actually have this fancy formula, so we don't have to do all that work we did up there. Okay, but this is only for p series. A's got to be equal to 1, and p's got to be greater than 0. Now remember, if p is less than or equal to 1, then hey, we just know it diverges, right? All right, so let's see if we can use this shortcut here. Okay, example 3, A, B, C, and D. Let's check it out. Oh, snap, this is definitely 100% a p series. It's a equals 1, so I can use that little shortcut right there and don't have to even do an improper integral. But 2/3, okay, 2/3 is my p, right? Whoops, let's write p equals 2/3. 2/3 is less than 1. If it's less than 1, what does it mean my answer is, class? It means it diverges, and it diverges to infinity, right, class? We had that in our notes up there. That was our fact. Okay, let's do the next one. Ooh, this one's interesting. It's a 1 right there. Oh, so I don't even have to do any of my work. I can use this little shortcut here. Well, for one, maybe on the AP it just says, does it converge or diverge? That definitely converges because my P is equal to 1.1, which is greater than 1, which means I know it converges. Now on the AP exam, they'll ask you, what does it actually converge to? So we have to find out what it converges to. So in order to find out what it converges to, since that A is a 1 and P is greater than 1, I can use that guy, which means it converges, okay, to 1 over 11 over 10, which is 1.1 minus 1, which would be 1 over, that'd be 1 over 10, which is 10. So believe it or not, that converges to 10. How about it? Let's look at my next one. Ooh, I better rewrite this one to make sure I look at it correctly. Oh, okay. That's definitely a P series. My P is equal to 7, which is greater than 1, which means I know that it converges. Now, can I use my super duper 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 whooper duper shortcut? I sure can. Why? Because that's a 1 right there. So then that's just 1 over 7 minus 1, which is 1/6. Oh, snap! And you are right. That most likely is going to be a multiple choice question, right? Hometown. Okay. All right. Let's go with this next guy. Ooh, I should definitely rewrite this one before I start it. So let's bring that 3 out. That's just a constant. I have an improper integral, which usually means I've got to do a lot of that extra work and bring out a limit and all that stuff, unless, of course, it's not a free response. This would be an example of a multiple choice. And guess what? It's a P series, and my P is 3 over 2. Oh, snap, that's greater than 1, which means this converges. Well, what the heck does this converge to? It converges to, I've got that 3 that I brought out there, and then be 1 over 3 over 2 minus 1, which would be 3, 1 over 1/2, which we all know is a sixer, right? 6. 1, 2, 3, 4, 5, 6. 6 in Nihongo, Japanese. Okay, let's keep rolling, class. It looks like we're doing a great job here. If I'm going fast, please hit that pause button. Okay, all right. This guy's definitely a little bit different. That's definitely not a P series, and this time it's improper because of the negative infinity. So let's just do work. But since it's not a P series, I've got to do it the old school way, right? And so this would be an example of maybe a free response question. Okay, so we do the limit, and I'm going to go from b to 0 this time, and I should probably rewrite that as 3 minus x, but that would be to the negative 1/2, since I'm going to have to do all of my work. So let's go. So that'd be equal to the limit. I'm going to go ahead and find an antiderivative. For some of us, to find this antiderivative, I'm going to have to use u sub. U would be 3 minus x. Okay, but if u is 3 minus x, that means du would just be negative 1. So I just would have to correct that. But this would be a power rule. So let's add 1 to it. I get a 1/2. Divide by 1/2 would be a 2. So that's how I get the 2. How do I get the negative there? Well, if u was 3 minus x, like I said earlier, my du would be negative 1. So I have to correct that. If you need to do u sub for this with side work, go ahead and do it. But it's going to be a big time waster. Okay, so we're going to work on being efficient with antiderivatives from here on out, especially with problems like this. Now, this looks pretty complicated, but here we go. We use the fundamental, negative, that's important. We use the fundamental theorem of calculus. So I have negative 2. Okay, let's plug in that 0, which would be 3 to the 1/2. And then minus, which is going to turn that into a plus 2. And then I'm going to get 3 minus b to the 1/2. Okay, what the heck does this end up being? Because now I'm going to go ahead and plug in a negative infinity, and let's see what we get. We get negative 2 square root of 3 plus 2, 3 plus infinity. Oh, snap. Easy peasy Japanese, right? That's just going to be a big bad boy infinity, right? Okay, let's keep on rolling. All right, got this little reading we got to do here. Integrals such as, oh snap, so it's just getting a little crazy on us here, where we could have all kind of infinities, and double infinities. What? Those are called improper integrals, class. Improper integral occurs in these 3 situations. 1, they have an infinite integral of integration. They have a discontinuity on the interior. This is part 1 of our improper integrals. We're dealing with 1. Okay, part 2, we're dealing with 2. Okay, they are evaluated by rewriting the integral as a proper integral. That's how we use that little limit, and using limits. Not every improper integral equals a finite number. In fact, you probably expect anything integrated to or from infinity will be infinite. An improper integral that equals a finite value, we say converges. Okay, we've already been going over that, to a specific value. An improper integral that does not equal a finite number is said to diverges, and it diverges to infinity. All right, so let's go ahead and look at a couple more examples here, okay? Example 5A, B, and C. All right, let's go ahead and do these bad boys. Okay, so we have infinity up there. That's an improper integral. That's not a P series. If it's not a P series, we got to do some work. So let's do it. The limit. This is the first problem we did, if you noticed, earlier today. Okay, but this time we're going to turn it into this improper integral. And let's see that. Now, if you remember from earlier, I think this converged, right, class? Let's see if it actually converges. Okay, we should be able to do it now mathematically, but not graphically. So let's go ahead and find the antiderivative. Okay, hopefully we're all okay with this antiderivative. We've been working with this guy a lot in A, B, and B, C. Whoops, 1 to B. Okay, let's go ahead and use our fundamental theorem of calculus. Okay, and your best bet right now is if you're feeling pretty okay with this stuff, see if you can do it on your own, right? That's kind of what we get there, right, class? Let's go ahead and plug in that infinity now. And so I'm going to get, ooh, snap. I'm going to get a negative e to the negative infinity, which that would be 0, right? Because that would be 1 over e to the infinity. And for this one here, I just get this, which, oh, snap, that's 1 over e. Go back and look at your notes. And remember, that's what we found that function there converges to, is 1 over e. Remember, I think it was 0.368. Okay, if you go back to that first page. All right, I'm going to go ahead and erase that. You guys make sure you hit pause if you need it a little bit longer, okay? But I need a little bit more room. Well, let's look at this guy. That's a little bit different of a graph. It still kind of looks like that, okay? So the question is does it get to the x-axis really close? Does it converge? Okay, and boom, we're that guy right here. Oh, snap, you're saying, Mr. Tanaka, that is wrong. It looks like that. Okay, and that makes sense because we're going this way, right? All the way to 0. And the question is does that get really close to the x-axis where it would converge, or is the area big where the area would diverge, right? After all, that symbol there means the area from the curve to the x-axis. But this time my improper integral happens because of the lower limit, which is a negative infinity. So we're going to rewrite this first. Okay, hit pause, try it on your own, see if you can beat me. Okay, we're going to find an antiderivative. It's really good practice, class, if you're doing it on your own, which would be 4e to the x over 4. You don't believe me, maybe you have to use u sub. Okay, but you can always check your answer by finding the derivative of that, right, class? And the derivative of that is that, so I know I did it, right? I'm going to go to b to 0 this time. Okay, now I'm going to use the fundamental theorem of calculus, which means I'm going to plug in a 0, which just gives me a okay, and then I'm going to do a minus 4e to the b over 4. Oh, snap, what's that? Oh, it's a negative infinity there. So let's plug this in, 4 minus 4e to the negative infinity over 4, which means that's in the bottom, which means that's going to be 0. 4 minus 0, that is 4. So that actually converges. So believe it or not, when we were thinking about what that would look like graphically, it does get to the x-axis so fast that it actually converges from negative infinity to 0. All right, one more on this page. Let's take a look at it. Oh, this one we did at the very beginning too. And remember, when we looked at this graph, it was that bad boy, and there was all of that area. So remember, this one diverged. So we better get diverge as my answer here. And let's go ahead and verify that using calculus. Okay, 1 to b, we're going to go as x to the negative 1. Actually, no, I'm not, because we all know that is a natural log, right, class? The antiderivative of that would be the natural log of the absolute value of x from 1 to b. Let's go ahead and use the fundamental theorem of calculus, which would be the natural log of b. Absolute value of b would be b because it's all positives, minus the natural log of 1, which is 0. So let's go ahead and, ooh, natural log of infinity, that would be infinity, so it does diverge. How about it? That totally worked out. All right. Now, as you may expect, okay, whoa, let's turn some BC into some AB topics, right? And here we're dealing with, what are we dealing with? We're dealing with volume. Okay, if we're dealing with volume, ooh, I better know what that looks like. I should know what that looks like. It's going to be a decay, so it's going to be like that. And we're going to go from 0 to infinity, so it's all of that. I'm going to revolve it about the x-axis, which means it would be a dx problem, right? And it's volume. Okay, and if I was to revolve it, right, if I use a different color here, it looks like that, which means that's a disk method. And disk method is pi r squared dx, right, class? And we're going to go from 0 to infinity. Oh, okay, cool. Right, that turns it from an AB topic into a BC method, right? Because I'm going to have to use an improper integral. Okay, so let's keep on rolling. We got our little limit here, and we're going to go from b to infinity, right, class? We got our pi that we took out. We're going to go from 0 to b. Now, what is my radius? Well, my radius is just the curve, which is that right there. So our radius is this guy here. Okay, and we're going to square it dx. Okay, let's do a little bit more math there, which would be the limit as b goes to infinity, because I should simplify first, right? Pi we brought out from 0 to b, and that'd be e to the negative 4x dx. Okay, go ahead and hit pause. See if you can beat me. We got the limit as b goes to infinity. Pi came out. Okay, we're going to go ahead and find the antiderivative, which would be a negative 1/4 e to the 4x, right? You should be good at this by now. Okay, from 0 to b, fundamental theorem of calculus. What does that bad boy say? Okay, the fundamental theorem of calculus says, okay, we're going to, that pi we brought out already, we're going to go negative 1/4. That would be e to the 4x power, or 4b power, right, class? Okay, and then what do we have here left? We have a plus. Okay, if I put a 1 in there, I get a 1/4. Correct, class? Oh, snap, I missed a little something. That's supposed to be a negative there, right? That's supposed to be a negative there, okay? So here, if I keep on going here, we're going to put infinity in there. If I put infinity in there, it puts it in the bottom, right? So I'm going to get a pi. So I'm going to get a 0, right? Because it would be negative 1/4, but it would be 1 over infinity, right? Which would be 0, and then plus a 1/4. If I distribute, I get pi over 4. How about it? So I was able to find the area of this dude that goes on forever and ever and ever. Why? Because it gets to the x-axis, that curve does, super duper quick. It actually converges. The volume converges for us there. Okay, let's keep rolling. Rapid fire. All right. These should kind of look familiar, really bringing some stuff together here. Oh, snappy dappy. Where are we at here? Let's get back to that. Where's my booyah? Where's my thing? Okay, we're going to pause it. Okay, let's tie some, let's have a little fun, get a little cray-cray, right? Let's tie some BC topics in together. And if you notice here, oh, snap. Believe it or not, that's integration by parts. Believe it or not, that's that one that was on our test. That guy goes on forever and ever, right? You got to just realize that one. And oh, snap, that's a partial fraction. Okay, we're going to do 2 of these, and you got to do 1 for your homework, okay? All right, here we go. Ooh, this is definitely a partial fraction. My u, lip it, right? Lip it would be my polynomial is here, and my e is over here. Okay, so let's take derivatives. It exhausts, so that was a good choice. Antiderivatives over here. Okay, right, class? And then, okay, I guess first I should maybe have turned this into a improper integral, b to infinity, of 1 to b, of 1 minus x, e to the negative x dx, okay? And that is equal to the limit as b approaches infinity, okay? And then I'm going to go ahead and find the antiderivative right here. Remember, I combine these guys and multiply it by a positive. So that'd be negative e to the negative x times 1 minus x. Good review right here. And then remember, I multiply these guys, but then I multiply it by a negative, right? So that'd be positive. So it'd be positive e to the negative x, okay? And I'm going to evaluate that from 1 to b. Okay, so that's pretty cool. Improper integral with 0, or tabular method in this case, right, class? All right, so here we go. Let's go ahead and use the fundamental theorem of calculus, which we have been doing. I'm going to plug in that b. That'd be, ooh, this is kind of nasty. 1 minus b, right? Plus e to the negative b. Okay. Ooh, and that's just the first little part. So I got to keep my organization really good here. Minus, now let's plug a 1 in there. I get a negative e to the negative 1. Oh, but then 1 minus 1 is 0, so that's going to kind of all go away. But then I get a plus e to the negative 1. Boom. Whoa, that's kind of long. All right, let's kind of use some shortcuts here. All right, I'm going to plug in an infinity. If I plug in infinity in here, you get something super duper small, obviously, but the infinity in there gives me a 0, right? Okay, so we're good there. If I plug in the infinity in there, it's e to the negative infinity. That gives me a 0. Okay, so that's the first little piece here, right? Minus. Okay, this gave me a 0 here. We already figured out because of the 1 minus 1. And then we have a plus e to the negative 1. Okay, if I distribute a negative sign, I get, what do I get? I get e. Oh, snappy dappy. Could I have done that right? Let's check my answers. Sweet! 1 for 1. All right, now this video is going to get crazy long if I do the next one. We've already done it in class, so your job as good practice would be to do that one again. All right, we're going to do C together. If I look at C, that's definitely an improper integral. As I'm doing the improper integral, though, I should notice that that is 100% a partial fractions. Why? Because 1, the degree on the bottom is bigger than the top, and 2, I have non-repeating linear factors, right, class? So there we go. I should rewrite it like that. Now let's go ahead and do the cover up, cover up. Let's do the cover up. Let's do the cover up. I don't know. Here we go. It's getting a little long, so I had to add some humor. Here we go. So let's go. Let's cover up this guy. That's a -3. So let's cover up that because a -3. So if I put a -3 in there, I get a -2. And 2 divided by -2 is -1. Right? It's -1. So if you notice, I'm just rewriting this problem. Okay, so it's going to be -1 over x plus 3. Okay, now let's go ahead and cover up this. A -1 makes that 0. So cover that up. If I put a -1 in there, I get a 2. 2 divided by 2 is 1, so it's 1 over x plus 1. Right, class? All right. Now that should be an okay antiderivative, right? That's just a couple of ooh, snappy dappy, don't do that. A couple of natural logs, right? Negative natural log, absolute value of x plus 3, plus the natural log of the absolute value of x plus 1, and we're going to go from 0 to b. Now that's kind of I should simplify that, because if I don't simplify that, I could make this problem super duper tough, okay? So if I notice that's a negative and that's a plus, so that means I could simplify it to the natural log of x plus 1 over x plus 3, right? Using my logs from 0 to b, this is going to be much easier to simplify now, and we're going to go the limit as b. I'm going to use a fundamental theorem of calculus now, which would be the natural log of b plus 1 over b plus 3, which is like infinity over infinity, right? Which would be 1, and the natural log of 1 is what? 0. Of course, now my pen runs out. Not bad though, right, class? Not bad for how long we were able to do that, guy. Because all I have to do now is plug in the 0. And if I plug in the 0, I get the natural log of 1/3, right, class? And then, like I said already, that's infinity over infinity, which would be the natural log of 1, which would be 0 minus the natural log of 1/3. Now, some people would say, okay, that means my final answer for that bad boy would be negative natural log of 1/3. But that, if it was on a multiple choice, wouldn't be the choice. Why not? Well, rules of log says you could do this, 3 to the -1. More rules of log say you could take that and bring it out front, which is the natural log of 3. How many of us would have known to be able to do that? I don't know. All right, here we go. Example 8. Let's keep on rolling. You guys are doing an amazing job. Let's go ahead. Example 8. Okay, some special situations that could occur. All right, I'm going to do A. You're going to do B for some of your homework. Let's switch it up. Maybe blue will keep this marker working a little bit longer. Okay, but you could have some of these cases that happen. Hopefully it makes sense. If you have a convergent plus a convergent, it would converge. Divergent plus a divergent would be divergent. Divergent and a convergent, infinity plus 5 is infinity. But if you get infinity minus infinity, what, right? Can't figure it out. All right, so here we go. Let's see, how would that pertain to this problem here? Well, that's not like a long division or anything like that, because the degree is smaller, bigger in the bottom. But what I could do, hopefully you realize, is, hey, you should split that bad boy up. And it is improper, so let's go ahead and treat it like an improper integral. Again, we're going to split it up. 2 over x squared, and that would be x over x squared dx. Okay, let's simplify a little bit. Okay, now we're going to go ahead and turn these bad boys into some negative exponents. 2x to the -2. And then I'm going to leave this as 1 over x, right? Because hopefully we all know, hey, that's just a natural log. So let's go ahead, and I bet you we're going to use one of those special situations up there. All right, so let's go ahead and look at this. What happens here? Okay, let's check it out. Power rule. So I'm going to add 1, which would be a -1, and then divide by -1. So that's a -2. Okay, this is plus a natural log of the absolute value of x. Okay, and we're going to evaluate that from 1 to b. Let's go ahead and use the fundamental theorem of calculatura. Okay, we plug in that, we get -2 over b. Okay, that's not too bad. That would be 0, right, class? Plus the natural log of the absolute value of b, which would be infinity, right? Okay, And then we have minus, we got to plug in our 1s. And if we plug in our 1s, what do we get there? We get negative 2 plus the natural log of 1, which would be 0. So if I do all of this, I get 0, right? Infinity in there will give you 0 plus the natural log of the absolute value of infinity, which would be infinity, plus 2. What is this an example of up there, class? That's divergent plus convergent equals divergent, okay? Your job's to do that one, and I'm going to give you a hint. You get infinity minus infinity, which means your answer would be indeterminate. All right, but this video is getting long, okay? And we still got to roll. Okay, so let's still go. All right, example 9er. Okay, I think we're 9, 10, and then we do the comparison test. I'll put it in the next video, or maybe we'll do it in class, all right? Okay, if you notice, it's a doubly improper integral. Ooh, I switched to the red. Please help out. When it's doubly improper, we do 2 limits. Okay, so here we go. And we're going to do this one from b to 0. We're going to kind of break it off. Okay, dx over 1 plus x squared dx plus, okay, we're going to do the limit. And this time I got to use c because c is going to represent infinity. And that's going to be 0 to c of dx. What the what? 1 over. Let's go 1 over because hopefully we're like, oh yeah, sweet. That's inverse tangent. Okay, so let's go ahead and do some antiderivatives here. Okay, which like I just said, hopefully you guys realize that's just the inverse tangent. Okay, and then you've got to be good at your trig skills. Okay, plus the limit as c goes to infinity. Once again, that's inverse tangent, but this one's going to be from 0 to c. All right, let's go ahead and evaluate using the fundamental theorem of calculus. Okay, and so we get that, and we get inverse tangent of 0 minus the inverse tangent of b plus the limit as c goes to infinity. And let's evaluate it. Fundamental theorem of calculus, inverse tangent of c minus, excuse me, inverse tangent of 0. All right. So in able to do this problem, I need to know what inverse tangent looks like, or I need to know specifically what tangent looks like. Remember, tangent looks like that. We have asymptotes. And remember, where do we have asymptotes? At pi over 2. Why? Because tangent is d and e there. And at negative pi over 2. So that's going to help us out quite a bit here. Why? Because let's say we plug in a negative infinity. Okay? Let's plug in that. Ooh, well, 0 is 0. Sorry, I got a step ahead of myself. That's 0 because it would be sine over cosine minus this is the 1. Okay, you're going to plug. Ooh, if I plug in a negative infinity, what do I get? Well, where do I approach negative infinity? And remember, inverse tangent has to be in the first or the fourth quadrant. So if you look at negative infinity, that's negative infinity, and it approaches that value right there. So we get 0 minus negative pi over 2. Okay, plus, let's look at that. That's a c there. So that's tangent inverse. When does tangent, remember, that inverse means your answer is an angle. Okay, so when does tangent, oh sweet, it went out. When does tangent equal infinity? We'll look at our graph right there. If we know our graph, tangent equals infinity at pi over 2. So on this one here, I get a pi over 2 minus when does tangent equal 0? At 0, right? Because it's got to be in the first or the fourth quadrant. And if I do my math, I get a pi over 2 plus a pi over 2, which is a 2 pi over 2, which is pi, right? Which is pi. Okay, now once again, to save some time, you guys are doing the next one on your own. And if you do the next one correctly on your own, you get an answer of 0. Now that is part of your homework, so you better be doing it. All right, I actually think I'll be able to do this last one here with you because it's a calculator, okay, because it's a calculator problem. But what they're asking us to do here is find the area of this region, okay, and the x-axis. Well, what the heck would that look like? Well, we're allowed to use our calculator, so let's get this bad boy out. Booyah! There it is. Now, what the heck does that look like? Well, remember, we have this fancy zoom box. I'm going to box this bad boy. Why? Because it's cool. Let's move that little, come on. Homie, hit it, homie, hit it, homie. Okay, go up. My video was supposed to be longer, just so you guys know, but I'm going to help you out. I'm going to cut it out here. We'll do the rest of it in class, okay? Or if I have time, I'm going to make another video. Boom. Okay, let's take a look at that. What would it look like if I zoomed in? Oh, okay. It gets to the x-axis super quick. So my guess is that it's going to converge. Okay, it's going to converge. Okay, so how could I possibly do this problem? Well, let's go back to our handy notes here. And if you notice, it's asking me the area actually from negative infinity to infinity of this crazy curve right here. Okay, but I'm allowed to use my calculator. So what are, sometimes we like doing these kind of a crazy way, but guess what? Maybe I should inspect it and just go from negative 100 to 100 of my function right there. And guess what? If you examine it, my answer is 1. And that's how you would do that when using the calculator. All right, here we go. Now, I didn't get as far as I wanted to. However, you still have problems in here that you better be finishing it off, okay? If I check those in class, that counts as a homework grade. I also, in your worksheets, I want you to do 1 through 6, 9, and 11, just in case some people say they couldn't hear me. 1 through 6, 9, and 11. So finish what we didn't do in here. Under 40 minutes, not bad. Okay, but finish those examples, and 1 through 6, 9, and 11, I could check it in class. Aloha.